Resume recording. So I've had some technical issues with sharing the recording. I have the recording of the third of the second lecture this week, but there was the issue that the file didn't store it on the cloud, so I don't have the link, and the file is too big to share on Moodle directly. I am now trying to figure out during next week or so. I will try to figure out how to put that in some university storage. But the thing is, with no one around, usually I handle this thing by going to the help desk and asking them to fix this problem for me. And now there's no one there, so I have to wait for email instructions, and that takes a little time. So I hope that you guys are patient with this. Was that, yeah, the Wednesday lecture, the morning compromisation was that fact that I was unable to go to the university. We were in full lockdown, and then I had to figure out a way to do the recording, and I didn't get before the morning, I didn't get the instructions on how to record these sessions. And then when I figured out how to do that, then I just put it on the afternoon. I don't know why there was, I mean, I used the same template and the same link, and it seemed to work, but no one seemed to, maybe there was a misunderstanding about the time, I'm not sure.
Well, there were about 11 of us, I think, in the lobby at, what time was it? I think at 2 p.m. But we were basically missing you at that point.
Okay, so I was giving the lecture there, but there was no one there. So maybe there was a wrong link or something like this.
Yeah, perhaps, because at least I used the one that was on Moodle. Like
I tried to do that, but I may have, you know, it was my first time using, I switched to another client to make this work. So a client software. So I may have had the wrong link in the client. So I might have made a mistake there. I was here, but maybe it was just the wrong link and the wrong meeting. So I'm terribly sorry about this. This technology is completely new to me. So if there were people waiting there, I'm terribly sorry about that. But now it seems I have the correct link and you have the correct link. So we're good at this moment.
Okay.
And
so
I will do my best in the future to make sure that it works correctly. This is, yeah, I was surprised that there was no one there, but I didn't think to change it, because I looked at the ID. So you are probably seeing the ID here at 394669816.
Not sure where we can see that actually.
Yeah, it's in the upper part, of the screen.
Yeah, at the below, but it depends on what kind of client you're using. If you're doing the, but that I checked that was the same as the one in my shared one, but for some reason it was I don't know what the problem was actually, but I have it on video. So once I figure out how to share that video, you will have the lecture available to you. I have it on my laptop, but I haven't still been able to upload it into any server where I can share the link. So I'll figure that out in the coming days. I'm terribly sorry about that. Just so that we get ahead with things, I'll just very quickly, let me just show you. I'll show you briefly what I talked about, so you can read it up on those. Just a second. So let me see if I can share, new share. You'll probably be able to see this now. This is the slides. Are you able to see this? I'm not sure how this sharing thing looks to you. So what we covered during that lecture, and you can find it when I have time to share it. I talked about a little bit about the correlation and the covariance, which I started already on the previous thing. I talked about correlation, There was the example. I went through this example. I put some intermediate results in the chat. I'll see if I can show them on the video. I talked it through this whole thing. Here were some interpretations of what correlation means and what it doesn't mean. I tried to explain that, and then went through these theorems where we proved certain things about independent variables. If you add them together, then you add the variance. I gave an example of this. If you have a variance of a sum of or a combination of two random variables, then you have to adjust it based on their covariance. So if the covariance is negative and the coefficients are positive, then in fact adding two variables that have a negative covariance that will lower the covariance. Then there was the Chebyshev's inequality. I explained that. The proof is not very hard. I explained the proof. What is the meaning of this? Compared it to some examples. There's some talk about that. And then I mentioned the moment generating functions. These are not, luckily, out of all the lectures that we had, with the possible exception of the calculating the covariance and calculating the correlations, that was the least important lecture in some sense in the whole course. So I'm glad that if we needed a problem to happen, then I'm glad that it was that lecture, because not most of these topics are not. I'm not going to ask you this moment. Sorry, about these moment generating functions in the exam. Okay. Now, are there now any previous examples or any exercises that have been puzzling any one of you that you want me to talk through here? Just stop that sharing and I'll share something else. I'll share the yeah, I'll share that whatever it is that we need to be sharing. But if there are any particular examples that were in the material that are puzzling you, we can check out if I can explain them better now, or we can. I just uploaded a new set of examples, and I've been doing the model answers now. If you want, we can go through those. I'll just look at this from just a second. Here, you should be able to see the third week examples, which I'm now going to share. There's a little bit of yeah, this is a little bit slow for me here. Wrong. That one. Okay, so here we had some examples for this about this week's material. Should be able to do this. So I have the model answers and I'll show them to you and we'll talk about those. But let's first look at these examples on how they reflect on the material. So mostly this is about calculating expected values and variances of various kinds of random variables that we can derive from random phenomena. The first example is a ball of 3 black balls and 3 white balls. This is classic probability theory, and we define a variable x to be the number of balls that we need to pick before we get, well, if we keep picking until a white ball is picked. So the sample space here and the density function here, we should calculate them. So before I go into that, I think we'll go through these questions a little bit first, so give some food for thought, and then I'll go through the how these are calculated. And at the end of this, I will share the whole thing in Moodle. So how do you go about determining the sample space of X? Here's a little bit of It's not, this is a very easy problem. So if we start with 3 and 2, so that's five objects in total. But if you notice that you pick until you get a white one. So if you start with 1, obviously if you get 1, you cannot have the white ball until you've picked 1, right? So the first one could be a white ball. The second, maybe it's a black ball. But if it's not, then the second one could be a white ball. So how many black balls left? There are 2. If you pick 1 black ball, then there are 2. After the second one, if you didn't pick a white ball, there's only 1 black ball. And on the third, after the third, there are only white balls left. So we know that the fourth pick is going to definitely give you a white ball. That means that in this case, the sample space consists of, well, 1, 2, 3, and 4, obviously. Now, in order to determine the density function, we'd have to calculate the probabilities of each of these occurring. Now you have to be really careful about what they are, the probabilities. A very common mistake in a question like this is to come up with an answer where you calculate the probability of picking 1, okay, and picking 2. So if you picked 1, I mean, let's say you start with the initial situation. So there are 5 balls, 2 of them are white. So we have f of 1 is something like, it must be equal to 2 out of 5, right? We all agree that this is the probability that we get it on the first try. So what is the probability that we get on the second try? Well, a very common mistake I've seen here, I'm trusting not many of you would make this mistake, but the very common situation is that how you are doing it the second time, you now have 4 balls left because you picked 1 that was probably black. So there are, well, it had to be black if you're keeping on picking. So there are 2 and 2 now left. So that's 2 out of 4. So that F2 equals 1 over 2. But that's not right, is it? And it cannot be right.
I thought it was.
Sorry?
I thought it was that, but like.
Yeah, but it's not. Why is it not? So this is the probability that if you pick, that's not probability x equal 2.
Do you have to integrate the F1 into the F2?
Exactly, because you are looking for probability that x equals 2. So if you picked it on the second try, then the probability that x equals 2 is in fact probability that x, there are 2 issues at here. First, so the event, if I write it here, event x equals 2, it consists of 2 events. It consists of x is, so first is not white, and second is white. So the 1 over 2 is simply the second is white, but it has to also consider the fact that you already had to have picked a black ball, right? So in fact, that probability that x equals 2 is in fact the event that you first picked a black ball. Well, that means that was 3 out of 5, and then you picked a white ball, right? That's how you do it. So we go and then by similar manner, the probability that x equals 3, you first have to pick a black ball, the second has to be a black ball, and the third has to be a white ball, right? So be careful with this kind of questions. These are very good exam questions, right? So if you see this, then be careful about how this is calculated, right? You have to understand that No, that's 3 over 10, isn't it? 3 over 5 times 1 over 2. That's 3 over 10, isn't it? Yeah. Yeah. Yes, let's carry on. Let's carry on a little bit. We can do the fourth one. So what would the F3? Can you give me what F3 is now? I mean, based on this, how would you calculate F3? F3 is the probability that X equals 3, right? So how do you calculate that? First of all, first one has to be black. The second has to be black. And the third one has to be white. So if you're having trouble with this kind of questions, then this is something that I really urge you to really go through in your mind and also on pen and paper to see. I'll give you the model answers and you should arrive at them, but yeah, before I show them all. Yes, that is correct. That is correct. So exactly, the first 3 over 5, that's a black one. Then there are 2 and 2, so that's 1 over 2 for a black one. And then there are 2 and 1, so that's 2 over 3, and that's the probability of X equal 3. And now we need to figure out anymore the X equal 4. Then we have the whole density function figured out, because the density function will be just f of 1 will be the probability that X is 1 and so forth. So in the third one, that's the third one. If you see the chat there, then Anna put there that 3 over 5 times 1 over 2 times 2 over 3. So what about the fourth one? So the probability that X equals 4 is, well, it's not 1, it's not 2, it's not 3. And then it's the fourth. So you get, first of all, the first one is 3 out of 5, obviously, like before, 1 out of 2 for the second one. And now in the third one, there's only 1 black ball and 2 white balls, so there's 1 over 3. But in the last one, there's just 2 out of 2, right? In the last one, there are 2 white balls left, so no matter which one you pick, it's a white one. And you can double check that if you add these all these 4 results together, you should get 1. That's a good way to check your answer. If you are asked to come up with a density function, then a good way to check your answer is to add them to, if it's a discrete situation, add them together, and once you've added them together, check that number is equal to 1. Or if it's a continuous function, then integrate over the range that you are supposed to have these values at. And if that integral results in 1, then that's probably, then that's evidence that you don't get evidence that it's false. If you get different from 1, you know that it's false. It doesn't verify that it is correct, but it does raise your confidence in the correctness if you check that it's 1. All right, let's move on to the second one. We'll go through these questions without the model answers first, and I'll show you the model answers. We'll talk about those in more detail than once we are done. So a dart is thrown, like we have the Tikkataulu example. We actually talked about this already in the exercises, so this is on, but now this is familiar, but now we are asked to calculate the density function f of x. So the density function then just gives you the probability for each of those I. We can come up actually with a closed form solution to this. It's not particularly hard. The thing about this is that if you consider the R, just for argument's sake, let's say that this dartboard has the radius 10. So each of these regions, the score regions, which are concentric circles, and if, again, if you calculate this 1 out of 10, between 1 and 10, those who know what we're talking about knows the outer circle is 1 and the inner circle is 10, but the nature of the problem doesn't change if you consider the outer region to be 10 and the inner circle to be 1. You get different results, obviously, for expected value and variance, but not in spirit. The spirit of the question remains the same. So if we consider the score region I, then you can think of this as that the outer layer of that region. Let me just do a new share, whiteboard share. So just, again, I'm sorry for the bad drawings. Let me see if I can make a circle here. So here's the, I'm cleverly using this technology. Oh, let's draw another circle. Oh, why doesn't it let me draw another circle? Let me just, okay, these are not going to be much better than my hand drawings, but at least they're roughly circular. Okay, that's not, yeah, that's not gonna be, I'm sorry. Just try to draw something that's, I'm just gonna make this for illustrative purposes only. These are not circles. Some of these are ovals, but you get the idea. So if we have here, this is the score region of I, right? And the innermost is the score region 10. That's your 10, and then there's I. And then the outer one is 1. I'm just gonna draw it like this. So sorry about that. Laugh all you want. I wish I had a pen or something to draw. So if we think about this in such a way that we can think that the outside region is 0 if we want. So if we want to think about this analytically, so the region of score region I, it ends at, well, it begins at, counting from the inside, it begins at 10 minus I. I mean, the radius 10 minus I. That's how far, 10 minus I, that's how far it is from the absolute center of that. So when you are talking about 10, it starts at 0. It starts at the origin. 9 starts at 9, and so forth. And the 1 starts at, 9 starts at distance 1, and the 1 starts at distance 9, and it ends at distance 10, so that the region ends at 10 minus I. I plus 1. Right? That's how you get it, right? So the circle, or the zone, or the score zone, then is delimited by these two, where the first one is a circle of region, the outer region is a circle of range, sorry, I wrote that wrong. That's 10 minus I plus 1. Sorry, I was 10 minus I plus 1, not minus I plus 1, because, you know, at the outer region ends at 10. So it's the area of that, let's call it area of region I is pi times, and then we have the 10 minus I plus 1 squared. And then you subtract the smaller one, that's pi times 10 minus I squared, right? So this would be, you know, that circle area is that 10 minus I plus 1 squared times pi, the whole, everything that lies inside, and then you subtract this surface area of this circle, which is the pi minus I, pi times 10 minus I squared. That's your AI. Oh, there's an equality sign. All right. This is what we get, and if we calculated this, let's do it simply. Let's mark 10 minus I equals x. I'm just going to do it. So this becomes pi times x plus 1 squared minus pi times x squared. So if you look at that, that's x squared. So that amounts to pi times 2x plus 1. Okay, where x is equal to 10 minus 1. So that's pi times 21 minus 2I. All right, that's the surface area of this zone region. And then the whole thing, we assume that this is a radius 10, so the whole thing has area 100 pi. So we get that Fi is, well, the upper one divided by the lower one, so we get 20 and 2I over 100. So that's your density function. No need to put it all in a table. You can put it all in a table if you want. I mean, just calculate each circle separately, but with this, a little bit of algebra, you can get the whole result. By the way, do you hear this terrible noise? Can you hear it from here? This kind of a humming machine-like noise?
Slightly, but it's
Yeah,
bearable.
it's my washing machine. Just give me a second. I'll say. Yeah, it's my washing machine. It's making a lot of noise. I'm terribly sorry about. All right. So everyone understood how this is done, this circle thing. I mean, I hope this is informative enough. I'll, like I said, there'll be the model answer as well, but I'd rather go through how this is derived instead of just throwing in the model answer, because the process is not visible. Okay. Let me just put this. Close that. And then go back to the examples. All right. So, oh, wrong. Well, here's the example. Let's just go through this. Here's the example from the first one. A little bit terse again. This crammed up this, but if we look at the sample space, we already talked about this. The first ball, fourth ball, and so forth. So here, oh, these are not. The table is again. I couldn't yet figure out how to make it a little bit nicer, but you get The first one is 4/10, the second one 3/10. We already calculated this, 2/10, and then 1/10. And what we do get is, in fact, that we can express this as 5 minus x over 10. And then if we calculate the expected value of the ball example, you can come up with add them together. So that's 4, and that's 3 times 2. So that's 3 times 2 from I, that's 6. And then we have 3 times 2 again from the I equal 3. And then we have 4 times 1 from the I equal 4. So we get 4 plus 6 plus 6 plus 4. That's 20/10. So that's 2. So the expected value is 2. So you would expect on average to pick 2. That's 1, 2, 3, 4. So on average, you have to make 2 picks. The variance, we can calculate the expected value of the square of x minus the square of the expected value of x. And this expected value of x is 2, so the square of the expected value is 4. And these we get, this is 4 times 1 squared. This is 3 times 2 squared, because there's 3/10, and then 3 times 2, 2 squared, 2 squared is 4. This is 2 times 3 squared being 9, so you get 18. And the last one is 1 here, because of the probability, 1/10 times 4 squared, so 4 squared being 16, and this amount to 20 plus 30, so that's 50/10 minus 4. Well, that's 5 minus 4, and it's 1. So here's variance of 1. So if you take the square root of that, the standard deviation is 1. So someone might say that how many balls do you have to pick? So that's 2 balls, give or take 1. So that's standard deviation. That's just doesn't mean much, but give or take 1. So 1, 2, 3 are the more common ones. 4 is only 1 in 10. And 1 is much more common than 3. All right, you see here. And then let's go through the circle example, which I already explained. We were asked to determine the density function of that. So I explained here that we assume that the radius is 10. So each score area has width 1. The surfaces of the score area is the outer circle, which I explained to be 10 minus I plus 1 squared times pi, and then this inner limiter is 10 minus I, and the surface area of the inner circle that is not part of it is 10 minus I squared times pi. And then I came up with this Fi equals 21 minus 2I. Calculate the expected value of the variance. I didn't do the computations here. F of I is equal to 21 minus 2I over 100. You can just add those together, the 2 times. You should get 385 over 100. Double check the calculation by calculating all of those. Oh, there's a typo here. Oh, I'm glad I didn't share it. So just a second. I'll share that shortly. There's a typo now. I realized for some reason the upper limit has become a multiplier there. That shouldn't happen. So let me just fix that very quickly. Oh yes, there is a missing symbol there, but that's quickly fixed. Oh no! Now can you see the difference there? Can you see the PDF should be I'm not sure if this works as it's supposed to. Can you see this expected value of x is the sum from I equals 1 to 10, from 1 to 10? Yes, good. So you saw that it changed when I did that, because I'm not sure how well this communicates with that. So when I change the file, does it immediately show to you? Because I don't see what it's sharing, but I'm glad it does show you that. So you see here, you sum up those from 1 to 10, and it's often easiest to calculate the variance in a way that you calculate the expected value of the square, and then you use the fact that the variance is the expected value of the square minus the square of the expected value. It's very common that this is much more easy computation than computing it with the directly from the definition of the variance. Either one is correct. You don't have to remember this trick of expected value of x squared minus the square of the expected value. You don't have to remember this, but it does make for an easier computation. So let's carry on. Before I share, I'll rather do it from this web page. So let me do a share of this one. Okay, so here we did the Tikkataulu example. So here's a random variable with a density function 3 over x to the 4. So where x is greater than or equal to 1. You can double check that this is in fact the density function. So what do we get out? Before we go, it's not asked here, but before we go into how you calculate this, and double check that it's in fact a density function. And the thing about this, you have to check 2 things. 1, it's non-negative, and 2, that the integral of it over the region that we're talking about is the integral amounts to 1. This is a little bit of bad wording here because it said it should be a continuous random variable. Continuous, because if I just say random variable with its density function and I say x greater than or equal to 1, it doesn't really tell you if it's a discrete random. I mean, what does it mean? Is it integers? Is it real numbers? It should say continuous random variable. But we'll do this with the continuous. It doesn't make sense if it's not continuous in this case. So let's calculate this. So it's very easy to do it. So if you think about it, you have to calculate the integral of this before go to calculating the expected value and the variance, to check that it works as a density function. We have to take the integral of this and let it go to infinity. So if we take the integral of this 3 over x to the 4, well, 3 over x to the 4, that's 3 times x to the minus 4. So the integral of x to the minus 4 comes out at minus x to the 3, because we increase the divided by 3. And then that's the integral of that integral of that function. And if you multiply that by 3, so it just amounts to minus x to the 3. And sorry, not x to the 3, x to the, so it amounts to minus x to the, I was missing a minus there, minus 3. That's I was supposed to have. And that is what it amounts to, the whole thing. And at infinity, that goes to 0. And at 1, that goes to 1, minus 1. And because it's the lower limit of the integral, then that amounts to, well, it amounts to 1. So it is in fact, definitely, clearly it's non-negative, right? When x is positive, then 3 over x to the 4 is obviously positive. Now, to calculate the expected value and the variance, what do you do with the expected value? Well, you multiply this with with x, right? So you calculate the integral of x times 3 over x to the 4, right? You calculate the integral of that, and that's just 3 over x to the 3. And the integral of that is minus 3 over 2 times x to the minus 2, right? And then at infinity, that's 0. And at 1, that amounts to 3 over 2. So you get, that's the expected value. For the variance, well, perhaps again, easiest to calculate first. The EX squared. That's easiest to calculate. So you have to integrate over x squared times 3 over x to the 4. But that's just 3 over x to the 2. So if you integrate that, then what you get is minus 3 over x. And then you get that expected value of, so that's that amounts to, the integral then amounts to 3. And then 3 minus 3 over 2 squared is, well, three over 2 squared is 9 over 4. That's 2 and 1/4. So you are left with 3/4. That's your variance then. Should be easy. This is the sort of question I would expect you to be able to do. I'll show you the model answer shortly. So, but it's not much more complicated than what I've just told you. I mean, I can't. If I had a whiteboard, I'd write here, but the shared whiteboard, I don't have the equipment to do the drawing. But I'm sorry about that. But you know, if you have any questions or anything, if you want me to show something in more detail, then fine, I'll definitely do that. Are any questions with this? Number 3. I'll show you the model answer now. How I did this. Share this one. All right, and go there. So that's just the integral there. It's just what I explained. You should be able to see this now. And these examples that we'll go through in the next couple of weeks, these are probably the sort of questions from which the exam questions are going to be. They may have different numerical values in them, but they're probably going to be the ones. Oh, sorry, again, there's just, I see that there's just, so easy to make these typos. Let me just fix that. Why is that missing? I must have done. That's a very common mistake that happens to me here. So I'm guessing that it's maybe the keyboard shortcuts that I'm using are working differently on my laptop than my, yeah, now it should be fixed. So there's the, I just cut corners a little bit, but not by much. So you just see the model answer, which I just explained. All right. Then we go to the next one, number 4. So it's a curious situation. So we have the continuous random variable, which is being given this density function, and again, should be no problem. I'm not going to go through the trouble of double checking that this is a legitimate density function. A legitimate density function would have integral of 1 over that region. I'm going to have to just assume that I'm going to take the word of anyone who has drawn this question for it and just assume that it is. When you model yourself something via a random variable and you come up with a density function for that variable, always check that that's a legitimate density function. If someone gives you a density function for a random variable, you could check that always, because you maybe should. If you have an exam question which says this is the density function, then if it's not, then that's that would be on me, right? That would be my mistake. But if I say check whether this is a density function, so then it might not be. Okay. But here, let's just assume that to calculate the EX, so you just multiply that with X and calculate the integral. So you have the integral from 0 to 2 of minus of X times minus 3 over 16 times X squared plus 3 over 4. The thing about this kind of thing, if you write it like this, so I'll write it like this, dx. So now if I copy paste this, if I copy that, let's see, I should be roughly then. This is cheating, but I'm going to do it anyway. I'm going to use the all-powerful internet. And now let me share that. What did I do? What did I just do? Well, I calculated this. You can see this? Of course, you can't use this. You're not allowed to use this. I am. I'm joking. You can use it to double check your answers if you do. So I calculate the integral here. I see that I get 3 over 4. That should be the expected value. Then I can calculate the, if I look at the example file there, which had the question regarding variance, okay, I can do it in one of two ways. I can calculate the variance by now, because I now know that it's 3 over 4, so I can put here x minus, is that 3 over 4? Why did I make some mistake here? It is 3 over 4, yeah. I can do it like this, so I put here 3 over 4 squared times. I can do this. If you see, you can see the window that I'm working on, because that's the formula of it. So I could use this to verify it, and I come up with 19 over 80. That's probably not. Is that correct? It could be. Doesn't seem to be what I thought it would be. Let's double check. So let's do here, let's put here x squared times that. And what do we get? We get 4 over 5. So I can subtract from this the one we got 3 over 4 to the 2. And I get 19 over 80. Yeah, I get the same thing. 19 over 80. That would be the variance now. I can do it like this. It's probably easiest to do by using something like this. But I do hope that you go through the trouble of going through the calculus. It's a little bit hard to show here how it's done. I don't have a proper whiteboard. I'll have to figure out a way. The suggestion by someone suggested to me that I should use the tablet so I can write that. That's a good idea, but haven't been able to procure one. In any case, this the one that is just computed, that's the first one, is the expected value of x squared, and then we just calculated the expected value of x. So we take the square of that and subtract, we get the variance. Okay. Any questions here? I'll share you the actual answers I came up with. Oh, I didn't compute the expected surface area. It didn't actually have the variance question here. It said that the expected surface area. I was reading it badly. So well there you have it. It's 4 over 5, the expected square. But we get, we get something for nothing. We get for free. We get ex squared minus the ex, well, the 3 over 4 squared. So we get the variance of x. But this question asked was somewhat different. It was the surface area of the square in question, if this is the length of the one side of the square. Okay, that's.
It might be a stupid question, but what is the diagonal stripe ranging from 0 to 2? It's not an integral sign. It's
that's that's the notification. So this means that there are various notes on how this is done. Very often, in what we do here is this diagonal stripe means that you've calculated the integral here. So this is this highlighting. I don't know if this highlighting is not working perfectly, but this you see here up at the upper here you have the x times, and then there's the minus 3 over 16 x squared plus 3 over 4 dx. So you integrate over that, and then that is that sign. It should actually be something like. I mean, many people have seen a different kind of approach. So let me just show you very quickly what I also mean by that. I'll add here something is equal to. Just a second. I'll edit it in the file so you see the meaning in a different notation. I'll edit the question A. Just hope that this works correctly. I wonder if this works correctly now. Let me just. Yeah, I know you use brackets. I know. That's what I'm. Oh. Why? Where did I make a mistake here? Just 1 second. I probably made a tiny bit of a typo there. made a typo there, so I couldn't get it to fall very well. Okay. Yeah. Okay, now. So that's the alternative notation is something like that. Is that the meaning? So you put it in brackets and then there's the upper and the lower. Sometimes it's put on the right, sometimes it's put on the left. So you put the once you've calculated the integral here, it's still sharing, isn't it? So once you've calculated this integral, the result of the integration goes inside the brackets here, and then this meaning that you evaluate it at the upper limit at 2 and lower limit at 0, you subtract the the lower from the upper, and what you get, that's what you get. That's an alternative notation for this. I actually think the bracket notation is better and less confusing because there's no delimiter here in this diagonal line notation. There's no limiter here, delimiter notation. This is a old notation, if you will, old school. I went to school in the previous millennium. That's when I learned this. This was thousands of years ago. This was I think the bracket notation is fine. Use whatever notation you are more comfortable with. I think I'll leave that bracket there just to show that that's the same meaning. Does that answer your question? I don't remember who asked the question about this notation. Yeah, C. Yeah, good. So you are more used to this this bracket notation, I think, right? Yeah. Okay. No. I'll try to make sure that it's a very good idea to always ask a question, because a lot of the times mathematics, you learn a slightly different notation and then it looks very different and it's confusing. But if you ask a question, what is the meaning of this notation, then sometimes you just get, well, you get, when you get the answer, you notice, I know this stuff. Okay, so now it shouldn't be too bad. But I do think, actually, in retrospect, that the bracket notation is less confusing because it shows clearly the limit of which x's do you do the substitution in. Now, moving on. We are shortly going to be running out of time, not yet, but I'm not sure if we have time to go through all of this. If we don't, I'll just share the ones that we have and get on with that. I'll go to this now. Share that one. Okay. And 5, a rectangular fence. Rectangular shape is fenced by picking up, well, fenced. Yeah, fenced, as in, that's I'm not sure if that's the correct word, because to fence means to deal in stolen goods. So a fence is someone who deals in stolen merchandise, and when you fence something, that means that you sell it for a fence, and you get money for stolen goods. When something is fenced, for instance, you can fence a stolen car. That's not what is meant here. A rectangular shape is limited from some area. We draw a rectangle. And I'll just maybe I'll share here. Share here. Whiteboard. So let's clear all drawings and draw a rectangle. So here's a rectangle. So we do a rectangular shape, and our x is one of these sides. So that's x, right? And that's my random variable there. And I'm I'm going to see that there is a certain, can you see both of these, both the drawing and the questions? Or do you only see one? I don't know exactly how this works. Do you see them both? All right, you see the drawing? All right, good. Then I will share this question. Now you should see the web page with the questions. Right, so it's good to know. You only see one figure at a time. Good. So we should calculate the density function of y, where y is in fact the surface area of the rectangle. So first of all, we need to determine the surface areas. How does that rectangle work when we have the x as the side of the rectangle? That's the side of the rectangle. So we have 12 meters of fence. So one side of the rectangle is x. So because that's one side, you need x meters of fence, but you also need, on the other hand, on the other side of that rectangle, you need x. So that's 2 times x plus, and then there's x 2 times 6 minus, is that the rest of that fence is 12 minus x, right? Divide that by 2, you get 2 times x, well, 12 minus x, that's so just very quickly. So x, one side is x, the other side is x. Those are 2 sides. Now what you have is 12 minus 2x. You have that much left, right? After putting these 2 sides. And then that has to be divided by 2 because you have, so the other side is 6 minus x. So what is the surface area of the rectangle? It's x times 6 minus x, right? So now we get this y, which is equal to x times 6 minus x. That's your surface area of the whole rectangle. Now we have to determine the density function of y. I think the best way to do this is to first determine the sample space of y. And because x gets values from 1 to 5, we calculate the different values of the sample space. So how do we do that? We calculate that y at different values of x. So when x equals 1, we get 1 times 5, so that's 5, right? So I write here that h of x is well, it's 6x minus x squared, right? That's my function. And now I go through x goes through all these values. So at 1, that's what? 6 minus 1, that's 5. At 2, that's 12 minus 4, that's an 8. At 3, that would be 18 minus 9, that's 9. At 4, that would be 24 minus 16, that would be 8. And at 5, that's 30 minus 25, so that's 5. These are the different results you get for y. So in fact, the sample space consists of 5 8, and 9. Only 3 values appear. 5 and 8 appear twice. You still follow me? So we now know that the sample space for y consists of 5, 8, and 9. So we need to determine the density function of y. We can do this by use of, we could do this if this was bijective using the bijection, but it's not bijective. So we have to figure out what is the g of y, this being the density function. So what is g of 5? Well, that should be the probability of y equal to 5. So we have 2 points where we have y equal 5, right? We have that at x equal 1 and x equal 5. So at x equal 1, that has the probability of occurring at f of x. So that would be 1 over 55. That f of x is x squared over 55 from the question. Plus then at 5, that's 25 over 55. So that would be 26 over 55. So g of 5 should be 26 over 55. What about g of 8? Well, that 8 occurs in 2 situations, when x is 2 and when x is 4. At 2, f of x equals 4 over 55 because it's 2 squared over 55. And at 4, it's 4 squared over 55. So that's 16 over 55. And the total is 20 over 55. And g at 9 only occurs at x equal 3. So that would be f at 3, and that would be 9 over 55. And to double check that this is in fact, we've calculated this correctly, we can calculate the 26 plus 20 plus 9, that would be 55. 46 plus 9, that's 55. The total is 55 over 55. So at least if we made an error, then we made another error which cancels out, because this g now seems to sum up to 1. So you add all these g values together, you get 1. So this should be the density function. There is no closed form solution needed here. It makes no sense to try and figure out a closed form solution here. We have these 3, we can list these 3 values, and this is the density function now that we have. That's our g of y. Okay. Here is the question: do we, using the fact that we can calculate h of x directly, calculate the expected value of y, and then check the result using the density function obtained in this first question. So let's remember this density function now, and let's just use the ehx directly. So we can do that by simply calculating the expected value of h of x. So that means that we calculate the sum over all these x's, and then we calculate h of x times f of x, and we add those together. We should get the expected value of y. So that would be at x equal 1, we already know it's 5 times 1 over 55. At x equal 2, you get 8 times and then 4 over 55, plus then at 3, that would be f of x is 9, and then you have, sorry, not f of x, h of x is 9, and f of x is also 9 over 55, plus then we have at h of 4 is 8, and f of x is 16 over 55, and then at 5 h of x is 5, and then f of x is 25 over 55. So that would be, let me just write this, e of h of x is equal to, here we have, so that 5, that's in this message that I sent, you can see that the first one, the first multiplier is the h of x, and the second one is the f of x, and we add those together, right? Alternatively, we can calculate the h of y as 5 times 26 over 55. So I just write it, e y is equal to 5 times that, plus then 8 times 20 over 55 plus 9 times 9 over 55. They should amount to the same thing. And that's not surprising that they do. If you look at them, then they do. In fact, of course they do, because it's just calculating the same thing with 2 different ways. Just double check. I'm not going to go through here with the particular value. This is how you calculate it, and then the sum, it's just very trivial hand computation doing that. Whenever we have a question like this, if you are asked to determine a density function, then if it only has a couple of values, then it makes sense to just write a table of them and be done with that. If it's easy to come up with a closed form formula for that, then fine, just do the formula, but it's not necessary. Of course, if it's a continuous, if it's a continuous function, then obviously you need to come up with a formula, because you cannot list, it's possible to list continuous variables. All right. We now have a question 6. A surface area of a circle is a random variable. Now, understand here that the surface area, just very good, before I go, I'll just share that model answer here. Here I did the same computation as I did, and I did calculate the values for, oh, there's a typo again, I see. Well, I'm glad I did. Why is there a minus there? It's 6 point. Yeah. That's roughly, when I write equal or I write approximately, doesn't matter. I usually don't like to use the decimals. I don't usually want to express them as decimals, but I just punched this into a calculator and got these numbers. They're roughly the same. Roughly, you know, they are the same. They should be the same. That amounts to 375, 1 over 55. You can add those together, those numbers, which we had there. 5 times 1 plus 8 times 4 times 9 times plus 9 times 9 plus 8 times 16 plus 5 times 25, it should amount to 375. I'm going to believe that it does. If it's not, then send me an angry email explaining why my computation was wrong, and I'll fix it. Now, you are all adults. We are all adults here. And, you know, sometimes there are, the answers are not sometimes perfect. So you have to be critical about these things and trust yourself a little bit, and don't trust your authorities 100%. When I say don't trust the authorities by 100%, I mean myself, not the health authorities. So please wash your hands and stay out of public for now. Those authorities you should listen to, but not me. All right. well, you should listen to, but you should be critical of what I say, because sometimes I make mistakes. All right, let's carry on. Let's share that sample. So we have the surface area of a circle, which is a random variable, and has a uniform distribution. Nothing hard about this. If we have a random variable with uniform distribution, that's 64 to 100. So there's 36. It has f of a. If I write it like this, is 1 over 36 when a in between 64 and 100, right? So we have this. It's 1 over 36. That's the length of the area. So you should be fairly straightforward. Now, what is the diameter of the circle? Well, the diameter is some h of a, and now we have to determine what that h of a is. It's probably easiest to understand that a is in fact the inverse of that d, and then that's pi times d over 2 squared, right? I mean, the diameter of the circle divided by 2, that's the radius. So pi times radius squared, that's the area. So we have here the inverse of that. So taking the inverse of that, well, that's easiest to say that's pi times d over 4, because if we do the, pi times d squared over 4. Yeah, that should be that. So we've determined this h now. And the inverse of h now, and we have figure out the h. Well, we calculate the inverse if a is this. We solve that for d, so we get that d is equal to 2 times the square root of a over pi, right? Multiply both sides by 4, divide by pi, take the square root, so you get 2 times the square root of a over pi. That's your h now. Now, how do we calculate the density function? Recall that this is a continuous function. So for the continuous function, and this is a bijective function, the diameter is always positive. We're dealing with positive values, so it's an increasing bijective function, and in this range. Because it's increasing, then it is a positive derivative, and the inverse also has a positive derivative. So what is the derivative of, so what is the derivative of the inverse? We need that. Because you recall that the g of d is in fact the f at h inverse at d times the absolute value of d over d. I can't use d, I have to use capital D here. I'm sorry, I used capital D here, but I'll just use x or y. I'll just use y here. I'll use y here. dy h inverse of y. So that would be your density function, wouldn't it? I mean, if y is the diameter, then that's your density function as per the statement we made. We can forego the absolute values here because we know that the derivative is positive because this is an increasing function, and it's therefore it's an increasing function, and therefore its inverse is always also increasing. Now, in order to figure out what this is, we have to find the derivative, but the derivative of this inverse is fairly simple. It's would be y times, so we get, well, if at that, the function is continuous, so it's 1/36 times f at the inverse of y, that's just 1/36, and then times the derivative, and the derivative is going to be, well, it's pi times d squared, so that the derivative of that is going to be pi over pi times d over 2. That's going to be that, because the f at the function at f at inverse h inverse of y, it doesn't matter that it's h inverse of y, because f is always 1/36. You multiply it by the derivative of the inverse function. In this case, the inverse function is pi times d squared over 4. Take the derivative of that, d squared, that's just d. Sorry, I was just using y, so this should be 1/36 times pi times y over 2, right? Yeah, so that's what pi times y over 72. All right, that's our density function there. The sample space must be calculated at the inverses. So we have the sample space will be, it's an increasing function. So it's at h at 64 to h at 100. It's an interval. It's a monotonously increasing function. So we can calculate at the endpoints, and it's the function's value at the endpoints. So this, if we calculate that and we put the 64 in place of a in the inverse, remember that the inverse function is that, that h function there, which we calculated to be 2 times the square root of a over pi. So at that becomes at 64, the square root of 64 is 8. And the square root of 64 is 8. 8 over the square root of pi times 2, so that would be 16 over the square root of pi. And at the upper limit, that's 100. You take 100, the square root of that is 10, so that's 2 times 10, that's 20 over the square root of pi. That would be your sample space for the diameter. And now we calculate the expected value and variance. I'm just going to share this shortly. There were some typos I had to fix. This skips a couple of steps over there, so the integrals are not completely Just 1 second. I'll share that example here. Okay, now you see here. There, that should be, you should be able to see that. So here, the uniform continuous, I did the same calculations here. I first calculated the inverse using the fact that the area is the diameter over 2 to the square times pi here. And then I calculate the diameter, and then I used capital D here to in the, just so that it's easier to calculate. So I came up with the same result, pi over 32 times D. The sample space, I calculated that H at 64 and H at 100, I get this. And then in order to calculate the expected value and variance, it's probably easiest to just calculate the integrals. I can throw them at the some software. We're running out of time, so I'm not going to go through all the details here. That calculus is not too hard. That's just a integral of a quadratic function. It comes down to a function though of the third power. So you would expect the pi's to cancel out, and then something over the square root of pi to remain, and that's what happens. The d squared, you know, you have the d squared there, so you multiply this with a d once more. So so yeah, there's that, and you will be able to calculate the integrals. I don't have the time to do this in detail now. We can look at them later a little bit. I hope that the calculus part is not too hard on you. I'm focusing more here on the modeling and on using the theorems that we talked about. If a calculus is hard for you, then that's something you need to rehearse a little bit more yourself. All right, we're going to stop here now. There was a 7th question, which I don't have the answer yet now. I will provide it later. It's about a random walker, starts at the origin, takes n random steps, each have length 1 in random direction. Each step is a random vector x1, y1, where xy squared plus y1 squared is 1, and it's otherwise it's uniformly random. In all the direction is random. And determine the expected value of the square of the distance after n steps. And you know, that's a bit of a tricky thing to do. It's going to require, I mean, I assessed that it would take me about 15 minutes to go through the example, so I opted to leave it at last, and we wouldn't have much time. It's a fascinating question, and I will provide you with a model answer in the coming days, but you can try to figure it out yourself in between if you want. I hope the 3rd week exercises per se were fine. I will open up the, after we stop this, I will open up the submission. I think the submission in Moodle is not yet working perfectly. No, it's not even working at all. Yeah, the 3rd, yeah, I will add the 3rd week submission workshop now, after this is over. I hope you will be able to submit your answers then. I will put the model answers to 3rd week questions on around Monday. And we'll have the Zoom session here. I really do hope that I can share these videos. I will be recording them, and I will share them once I figure out how to share the video. I only have it seems impossible for me to get the cloud recording. It seems to always just record it on my hard drive, so I have no idea yet how I could change that. But if I find a way to share that, I was shown by a friend some way, but I couldn't yet figure out how to do that. But I will figure it out, and you will get these sessions.
And are the exercise sessions going to be recorded as well?
I will record them and I will do my best to share those recordings as well. Yeah, I
Yeah.
will
Okay.
try to do
Thank you.
that. The problem, of course, being when I figure out, I will share them. But yeah. Yes, that is true. It can be shared via link, and that is true. But yeah, I'll see. I'll see if that's true. By the way, I can share it over OneDrive. That's actually a good idea. I can share it in the OneDrive. I'll do my best to figure out the way to put that link so that that it's visible only to you. I haven't used it in sharing the student material for students of a particular course, but yeah, that could be a solution. Thank you for the suggestion. Any other questions now? Anything you might want to know about this thing? Anything that's nothing? Okay. I think we can finish this session at this moment, and I wish you all a pleasant weekend. I truly hope I can get this technical issues ironed out so that we can keep on doing this in a more fluent manner. I hope this wasn't a complete disaster from your point of view. And I hope to see you on Monday. And on Tuesday, I will have the lecture at the scheduled hour, 10 to 12. And Wednesday, I'll make a poll. Let's say I'll make a poll of all those who attend on Monday and Tuesday or something like this. I'll try and set it up so you can vote about the times at which we can do. I could do it at 8 o'clock in the morning. I will have kids over here, so that's going to be a little bit of a challenge, but we'll figure it out. All right. Okay. Stay safe and have a nice weekend.
Thank you.